Hello students, welcome you all to the course of Compiler Design. In today's lecture, we will be studying about data flow analysis. We have come to the last phase of the compiler and we have already generated the code. We have seen the various code optimization techniques. So now it is good to understand how the data flows through the program. So that is what we are going to study under data flow analysis. For the logic of the program to be correct, we should know whether the assumed data or whatever we are planning to have written the program for is working correctly. So we have to check the data flow of the program. So that comes under data flow analysis. So as you all know, a program is nothing but an execution path. So from one point to the other, the flow of control is passing through. So we can assume each of these points as P1, P2, Pn and so on. And every point is going to precede the statements with the following set of statements. And we have already studied the concept of basic blocks. So all these statements together are not continuously written, but we divide them as basic blocks so that we have a predecessor and successor. So the block will be starting with a statement, ending with a statement, and so on. So infinite number of paths are available. We know that there are going to be if conditions and various other logical testing will be there in the program, which may take the program to different paths. So in all the paths, we have to take care that whatever logic we have mentioned for the program is kept intact. So that is what we are going to analyze and find or how it works. So mainly this data flow analysis will be used for debugging. It will be very useful to debug the program, whether the correctness of the program. This is otherwise called as the reaching definitions. See, we may be reaching a program point. So up to this point, whether it is working correctly or not, whether the variables definitions are correct. So that is why it is otherwise called as a reaching definition. And this whole algorithm can be defined as a reaching definition problem. And further we can, if I know the data flow, I can also use it for optimizing the code. Some of the code optimization techniques like what we already studied, constant folding, copy propagation, common sub-expression elimination, all this, it will be easier if I know the flow of data. So analysis of flow of data in control graphs is the analysis that determines the information regarding the definition and use of the data in the program. So with this help, as we already mentioned, optimization can be done. And then the technique is used in compiler design to analyze how the data flows through a program. So by tracking the value of the variables and expressions, they are computed throughout the program. We achieve the goal of identifying opportunities for optimization and identifying potential errors. Further, the basic idea behind this data flow analysis is to model the program as a graph, where the nodes represent program statements and the edges represent data flow dependencies between the statements. And then the data flow information is propagated through the graph using a set of rules and equations, which we will soon see, to compute the values of variables and expressions at each point in the program. So the scheme consists of a flow of control. We are going to mathematically model it as a reaching definition problem, and the domain for that is all the values, the variable values. Okay, and it will be a set of all subsets of the definitions in the program. So whatever variables we have defined, so we are going to take everything and put it at a subset. So there are some basic important functions which we will be dealing with. There is something called an in and an out. Okay, so the data flow values before and after each statement, that is called as in and out. So we'll mainly concentrate on these two functions. There are two more functions also which we will see. So the problem is, the reaching definition problem is defined as such. So we have these equations. So I told you there is an in function, and this is a union of all the predecessors of a block B. See, all these capital letter B refers to the blocks. So in any block, what is coming in is nothing but the predecessors of B, what is our from the previous block. Okay, and it is going to be taken to the out of B. So all this will be also going out. Similarly, out means whatever was generated, and then you union it along with the incoming variables and one more function called kill function. So what does the gen function and kill function do is, gen function is the set of all definitions inside B that are visible immediately after the block downwards exposed definition. So whatever is getting generated in the block, that is called as gen function. And whatever is kill is union of the definitions in all the basic blocks of the flow graph that are killed by individual statements in the particular block. See, as we see the example, we'll understand better. The kill means, supposing there is a variable in block B1. If the same variable is getting defined in another block B2, which means the value of the variable that was declared in B1 is killed. It is no more valid. So those type of information we will also analyze so that we know which is the current value for the variable. So you can see this particular example. This is in pass 1. So it will undergo 2 passes. Basically, this is a flow graph. We have an entry point and an exit point, and it consists of blocks. So here there are 4 blocks. So in every block there are some computations done, and there is something coming inside the block, going outside the block. So all these are represented by the 4 functions what we studied now. So we will take the first block. In the first block, there is nothing coming in. This is the initial block. So we don't have in function here. So in function is null. Okay. And if we analyze clearly, in the pass 1, for all the blocks, in function will be null only. Okay, you can see here. We are not going to consider what is coming in, and only we will be interested to see what is happening within the block. We are not going to see the entire flow. In the first pass, we will see whatever is happening within the block. So in this B1, what are all getting generated? D1 is D2 and D3. They are being generated. That is why gen of B1 is D1, D2, D3. Then we are in is null. What is coming out of this? Whatever is generated is coming out. So we are having out of B is D1, D2, D3. What about this kill? As I told you, if the variable is getting redefined elsewhere, then that is defined as kill. So here in D1, I is created, J is created in D2, A is created. If I take I is reassigned in B2. You can see here D4 is I equal to I plus 1. It is redefined. So in kill we put D4. I is getting reassigned in D4. Similarly, J is getting reassigned, A is getting reassigned in D6. So that also we include. And here J is getting reassigned in D5. So that also is included here. Again, I is getting redefined in D7. So D7 is also included. So whatever variables here, if they appear in other blocks, it means that it has been reassigned. So those things we have to write under kill. Now coming to B2, the same thing happens. What is getting generated? D4 and D5. What is in? In is always null in the first pass. What is out? D4 and D5 itself. And then kill, if I take, I and J are getting reassigned in D1, D2 and D7. Okay, here only I and j are there. So those things we are writing here. Similarly, if I come here, we are generating D6 alone. Output is also D6. In is null. Kill is A is getting reassigned in D3. So that is why we put D3 here. It is a loop. So wherever it is reassigned, we have to include. Okay. So this happens in pass 1. Similarly for B4 also. D7 is getting generated. Out is already D7. And then kill is the I variable is getting reassigned in D4 and D1. So D1 and D4 we have included here. Is that clear? We have only four functions: in, out, gen and kill. In is null in the first pass, so we don't need to bother about that. Out is whatever is coming out of the block. Whatever is generated will be the out. In pass 1, gen and out will be the same. Only part we have to look into is the kill function, which we have to analyze whether the variable is getting reassigned in any of the blocks. Then we have to write that particular variable name. When we come to pass 2, we are going to consider the flow of the data also. So now gen is the same, D1, D2, D3. Kill is also the same, whatever is getting killed. In is initially null for the first block. Out is the same. But when I come to the second block, what is in? In is, what is generated is D4 and D5. And kill will be the same. What about in? In is changed now. In is whatever is coming inside B2. So that is D1, D2, D3 from B1. And there is an arrow here which is bringing D7. So D7 is also included. And out is now whatever is getting reassigned, along with that whatever is not reassigned also we have to take. See, from B1, A is not reassigned here. So that has to be carried forward. The flow of data is like this. So we are having D3, D4, D5 from here, D3 from B1. So that is the difference in pass 2. In pass 2 we have to consider this flow. So now coming to B3, it is generating D6. It is getting killed in D3. So gen and kill will be the same. In and out will change. So in, what are all the things coming? We have to take like this. In this arrow, D3 is there, D4 and D5 from here. Okay, so in is coming here. And then out is whatever is following. So D4, D5 and D6. Similarly, when I come here, in is D3 is coming, D4, D5, and from this side also D6 is coming. Okay, all the in will be taken in. And then out is whatever is carrying forward. So D3, D5, D6 and D7. So that's how we have to assign the values in pass 2. So in pass 1, in will not be changed. Gen and out will be the same. Kill alone we concentrated and found. But here gen and kill are the same. In and out we have to manipulate according to the value coming in or going out. Okay, so the final thing is what we already saw. So we are generating, and the kill also we have to take in is null, out is D3, the same thing only. Okay, so this will be the final pass. This will be the final value what we obtain. So we are following the algorithm like this. For every block we are finding initially in is null, out is the gen value, that is what we saw in the first phase. And then we are having a Boolean function and while do change. So we are doing it repeatedly. For that time only we are taking the predecessors of B. So in will become the predecessors of B and out will be combining what is in gen with the union of in minus kill. Okay, so the loop will be done repeatedly. That is how we got those values. So we followed this algorithm and got the values for gen, kill, in and out. You can also note down this algorithm and analyze with the diagram. So we orally did that. Actually, we are following this algorithm and computation only. So both will match. Okay, so once it is done, I can go for my live variable analysis. So what are all the variables live here? Whatever is getting computed is live. So m, n and u1. Similarly, what are getting defined? I, j, a are defined. Whenever I assign values, it is the definition part. And what is the in part? All these variables, see, all this should have come in m, n, u1. That is why we have written it. And u2 is used somewhere here. So all that must be entering. So that is why u2 is also included here. And what is coming out of b1? I, j, u2 also we have entered, no? So that is why we are including u2 also. I, j, a and u2 also. Because u2 is not defined here, but it is going to be used here. So that is why we are bringing it in the out of it. And then when you come here, in is I and j only are needed here. So that is why in use means what is being used in the block, what is getting defined. Okay, in B2 actually nothing is newly defined. Already in only, that same I only we are writing here. Whereas here there were new variables, no? So that is why the definition part was there. But here it is the same as this. So we are not changing it. And then what came in is I, j, u2 and a. What is going out is u2 and a, because I and j have been reassigned here. So it is assigned here. So what is left out only will be coming out. So similarly, it is done here also. Use is, now we are using u2 here. And definition is a is getting defined newly. So that is why we are writing a. And the in part is what is coming inside here, and so on. So the live variable analysis also can be done. So we can know which is alive, which is not alive, which is in use. All these important analysis we can do. So mainly we are able to identify the dependencies, which variable is depending on which other variable, and then detecting dead code. Any code that is not required, which is repeatedly done, we can find out by doing this analysis. And then it can also be used for optimizing the code, because now we have a full analysis or the understanding of what are all the variables in each of the blocks. So that way it will be helping us to optimize the code. Unwanted code we can remove. And also if there are any errors in the logic we have written, the program computation, the initializing of variables, all this we can detect. And then any complex control flow. If we find that the control flow is complex within the loops, we can try to make it simpler. And then interprocedural analysis. We are talking about blocks. So from one block to the other, interprocedural analysis also can be done. And then the scalability of the program. If I do a data flow analysis, it helps in scaling to large programs. Whatever is true for this prototype analysis, what we do is also applicable to a larger program. So scalability is also enhanced. So these are some of the advantages of doing data flow analysis. Thank you.